Okay. Good morning. My name is Cassidy Ellis, Local Government Program Manager for SPEER and Manager of the City Efficiency Leadership Council Program. Thank you for joining us this morning at our slightly modified time slot for our Strategic Energy Management discussion on water and wastewater systems. As usual, going to get started with some program announcements and information. So for those that are new to the webinars, City Efficiency Leadership Council is, I mentioned, the program I operate in partnership with the State Energy Conservation Office and HARC. And we are focused on bringing Texas cities and other public entities together in collaboration around energy management and energy efficiency best practices. We get together in in-person roundtables through these webinars and development of other resources and tools. If you're interested in getting involved, please let me know. We have a couple events coming up pretty soon, so it would be great to see some of you there. So, let's see. So as I mentioned, we have a couple of our roundtables coming up. So Thursday, December 5th in Pearland, we will be hosting our Gulf Coast Roundtable. And then the following week on Wednesday, on December 11th, our Central Texas Roundtable. These roundtables are our primary in-person gathering. They are only open to our public sector participants. And they are an opportunity to learn a little bit more about new information, maybe new information to you, and network a little bit. So looking forward to those. Some of you also know about another extracurricular that I sort of participate in on behalf of SPEER, and that's the Energy Services Coalition. This is a public-private partnership industry group focused on education and outreach around energy savings performance contracting. And we are having our chapter meeting, which is open to anyone and everyone for free in San Antonio on December 4th. That's a Wednesday from 2 to 4. I will be skipping December webinar next month. I'm taking a break for the holidays, and we will be back in January, hopefully with some new and exciting content. Also going forward, I am trying to, I am able to prepare certificates for anyone who participates in these webinars for your own self-reporting of CEUs. So webinars will not at this time be aligned with any specific credential, but if you have a PE, lead AP, CEM, and you need self-reported hours, I can prepare certificates for you. So let me know if you need that, and that will be in the announcements following this webinar. For anyone who's unfamiliar with our controls here, if you go to the bottom of your screen, there is a Q&A button. Please click that and type in any questions while we are going through our webinar. And as always, we'll have a Q&A process at the end. So with that, I'm going to jump in to introduce our speaker, Matt Jensen, who is a Strategic Energy Management coach for water and wastewater systems with Cascade Energy. SPEER is very proud and happy to welcome Cascade Energy as our newest member, and very glad to continue the conversation around energy and water, and continuing on our webinar from last month on the energy and water nexus, and not only the value of data in making energy decisions, but how this can also impact water systems. So with that, I am going to stop sharing and let Matt take over controls and jump right in.
All right, thank you so much, Cassidy. I hope now that everyone can see my screen.
Yes, you are good, and we can hear you.
Excellent. So my name, as she said, is Matt Jensen. I am an energy efficiency engineer and SEM coach for Cascade Energy, which I've got branded here as well. As we started co-branded kind of our outreach to water systems as aqua efficiency with a partner engineer. So I've got that branding as well on the screen. This, I should mention, is largely, this presentation is largely taking off of the presentation that I did at the ACEEE conference in Portland this last summer in August. And if you're interested in reading the paper that went along with this report, I would encourage you to look that up on their page, on their webpage. So let me make sure my screen is advancing. There we go. So dealing with water and wastewater and SEM. Of course, we live on a planet that has a ton of water. There's water everywhere, but most of it's not usable to us. And it takes a fair amount of energy for us to collect that water and treat it in a way that is therefore that we can use it then to support human life. And that energy was largely, it wasn't pretty focused for a lot of years by the energy efficiency community, and only maybe in the last 10 years have we realized that there are a lot of gains to be made in water and wastewater, and so a shift of focus has happened, which has been a lot of fun. So I guess the first question is, what is SEM? That's the acronym for Strategic Energy Management. Strategic Energy Management is a focus on identifying low and no cost operational changes and improvements. It really talks about creating a culture change towards focusing on energy efficiency, and not just buying the newest and latest gadget that can save energy, but really just taking a holistic view of how water systems and wastewater systems or industrial processes work, and then finding ways to have them operate better and more efficiently. And so there's a lot of components that are affected by SEM. I've listed 5 or so here that certainly come out of the SEM process. But the main thing is to work with the existing operators, water and wastewater operators in the case of water and wastewater, utilizing their expertise on their system. They are the experts of their system, and through them finding better ways to run things where we can save energy without spending a lot of money. So here are the steps to the SEM process. Creating an energy policy is huge. Assembling a team. We conduct a series of workshops, and I'll have a slide where we can explain the benefits of those workshops. We do treasure hunts, and these treasure hunts, that's what we call them, but they're akin to what you might be familiar already with, where someone comes in and performs an energy efficiency audit for you. Those are very similar. However, they're much more effective through the SEM process because of the supported components to helping implementation. And then, of course, implementation of those findings from the treasure hunt, and then a measurement process as well. This is what I've laid out here in front of you. This is the SEM process, and it's the SEM process in industrial, for industrial processes as well as for water and wastewater. However, in this presentation, I want to point out the unique features of water and wastewater that allow them to embrace SEM in a way that is sometimes difficult for a mixed industrial energy cohort. Really, water and wastewater is made for SEM and vice versa. So there was a report done by my colleague, Dr. Rob Sobey, where he identified that that there's a collaboration between having an energy policy in your organization and less energy use. And he found that organizations, this was correcting for size and complexity and location, that just if an organization has a stated and written energy policy, they typically use about 30% less energy than similar organizations that don't have an energy policy. So one of the first things we do is we encourage our participants to create a written policy stating their intent to save energy and to focus on that and making that a priority. And we find that most water systems already have a mission statement. And one element of that mission statement typically is something about providing this, water at the lowest cost possible. And yet that's usually an area that is overlooked by water systems because they're mostly focused, and rightly so, on providing clean and safe drinking water. Or in the case of wastewater, clean and safe outfalls back into our water sources. And usually there's a mindset among water operators and wastewater operators that cost is secondary, that the primary focus is maintaining the public health. And that's a good place for them to have their priority. And we try to help them understand that it's not mutually exclusive, that typically as you operate your water and wastewater systems more efficiently, the quality of your product also goes up. The next step is to create a team. So this should be a broad representation in your organization. We want people, we want mechanics, we want operators, we want engineers, we want administration. Everyone has a different view of their operation and how it works, and it's best to have all those views represented. But there are three key positions that we encourage or that we require. One is to have an energy champion, someone where this energy initiative is part of their job, and that person is our primary contact when we're working with the cities or with the wastewater plants. They're the guys that are keeping this in the forefront of team meetings and presenting results and helping to drive change. There needs to be an executive sponsor, someone who is stating clearly that this is a priority, that we are going to make sure there are man hours allocated to this effort, and removing any administrative barriers to success. And then because SEM is very data-driven, there needs to be a data master who can collect data and supply that to the energy team and to us as coaches that we can work with to create a model and to help them help convey results. The next step is once the team, we create the team through the workshop process, but we have a series of workshops, and this is across SEM. This happens, but this is where water and wastewater systems really shine. That water and wastewater operators love to collaborate. They love to find out what the next city's water system, what they're doing, or what the next plant's doing, what technologies they have. They love to talk about problems they're having and identify solutions that have come from other organizations. And oftentimes with mixed industrial, you can't have, for example, two pulp and paper mills on the same SEM cohort because they see each other's competitors. But thankfully, water and wastewater systems do not see each other's competitors. They see each other as peers in the organizations, this broader organization of treating water. And so helping them network through these workshops is really great. And we actually see participation maintain or increase over the course of the engagement when working with water and wastewater, whereas typically in industrial cohorts, you'll see participation start to wane a little bit as it goes on. So the beauty of the workshop, there's a couple benefits. One is we teach them the stuff that we're going to use at the treasure hunt or at the audit. So there's no tricks when we show up to the treasure hunt that they haven't already seen in the workshops. And because of that, they're more invested in the solutions that they and us collectively are finding. We run through some sample problems from the DO. We talk about typical opportunities that we find in water systems and help them understand that if they have these things, there's no shame involved. Everyone does them. And so, but it's because, as I said before, people are focused on treating water. They see themselves as safeguards of public health, and they are. And energy is typically not even something that's considered. We work on problem solving, we brainstorm ideas, but the other beautiful thing that comes out of workshops is there becomes a positive peer pressure. And as the workshops continue after the treasure hunt, there is it helps people to feel motivated to implement change when they know that one component of the next workshop is reporting on how things are going back to their peers on the things that they've implemented. And so the workshop environment is crucial to getting people to implement the changes or the opportunities that we find in the treasure hunts and the audits. And some groups that we've worked with in the past are excellent at doing audits. I say engineering groups. where they'll come in, they'll provide a beautiful report with a list of changes that should be made to save energy, and they find that the adoption rate of those energy efficiency opportunities is very low. And the reason is because outside of the peer networking and the peer support and the training that happens at the workshop, it's very difficult to get water and wastewater operators to make the changes. And so within the broader scope of SEM, we are able to, that these treasure hunts or these audits become a very effective tool because of all the supporting elements of the SEM process. And then, of course, we go on site for the treasure hunt. And this is really driven, we lead it, of course, but the ideas are driven by your teams, by the teams of the water and wastewater operators and engineers and administrative staff. We go on site, we do a tour of the plant, or we do a virtual tour of the hydraulic model. We talk about things, we ask questions, and in the end, we brainstorm ideas. And the power of the treasure hunt is, at this point, the operators they've been taught the key things to look for in saving energy. They understand the difference between demand charges and regular energy charges. They've become, through the workshops, they've become prepared to participate and collaborate, and the ideas that we generate about their systems are their ideas. And so because they're their ideas, there's a much higher likelihood that they will implement them. So this is usually a day-long event, or in some cases we're working with right now the city of Phoenix, which is a massive distribution network, and we're working with 4 of their water plants plus a distribution network, and we did one treasure hunt at each of the plants, and then we did a 2-day treasure hunt of their distribution network because it's just so large. And then my colleagues that were overseeing the wastewater side similarly did their treasure hunts at the wastewater plants. So we scale these to the size of the organization that we're working with, and so that we can make sure that we give a thorough review. And then, of course, comes implementation. So there are some things that we can help with implementation. As I mentioned, there's coaching on our side. There's we do to help people make the right decisions, the right choices. There's check-ins, but really the action happens because by this point the operations their operation team is bought into energy efficiency as a goal, and they started changing their culture to focus on that, just like people in organizations have gone through a lot of effort in the past to create a similar culture around safety. And so we talk about that. Hey, that this needs to be something that you're talking about in your team meetings that are brought up regularly, and that you're soliciting ideas from everyone in your organization. And then the measurement piece is very important. So we build for as part of this, we build an energy model of the organization's operations. So we will look and see, let's say in a wastewater plant, we'll create a daily model. We'll look at BOD, and we'll look at influent and effluent and chemical addition and a whole bunch of number of variables. And we will compare those variables to their energy use. And we will identify the key drivers of energy. And then we will build an energy model that matches their current energy use with their historic energy use with those historic parameters. So then once we start going forward, we can show, after they make changes, a deviation from whether the energy they would have used had they not made a change, because we've created a model that does that. So in the end, we can quantify exactly how much energy they've saved, and we can create for them a report that tells them, these are the changes that you made, and here are the results. This is the actual energy saved. And we send those out monthly, and we help them celebrate the successes because there are data that show their successes. So that is the SDM process. Now let me go through and talk about some of the case studies where we've implemented this and had some fun success. Oh, let me show you this map first. So this shows an area where we are currently implementing water and wastewater SEM. As I mentioned before, there's 2 dots down in Phoenix. Phoenix is the largest city that we've engaged with so far. We've got a multi-year engagement with them, and it's been a lot of fun to tackle such a big opportunity and a big challenge. But we're having great success with their plants and their plant operations as well, for water and wastewater, as well as their distribution group. You might notice that in SPEER's footprint, we have not had any SEM engagements, and we're hoping that will change sometime in the future. So, a couple case studies for you. First one I want to mention is a water. This is a Jordan Valley Water Conservancy District is a water wholesaler. So they collect water. They buy water from Central Utah Water. They've got a ton of acre feet that will allocate to them out of the reservoirs up in the mountains, and then in addition to that, they have a ton of wells, and just a number of wells all over Utah Valley and Salt Lake Valley. They bring water into the Salt Lake Valley as the primary customers are in that area, and they wholesale to cities all along the Wasatch Front. We worked with them. They saw a 25% reduction from baseline. They were a solo XCM engagement, a big enough group that just like having different divisions of their organization was enough to create a peer group for our workshops. This was, I should mention that, there's a picture in the background of Rocky Mountain Power. Rocky Mountain Power is a local utility who helps subsidize this engagement with Jordan Valley, and they gave them incentive check. You can see the incentive check in the background is the largest to date of any incentive check that went to this water district based off the energy that they saved through this engagement. There's a number of articles for it. There's one of them you can see. The main thing that they did to save energy was what we refer to as source selection. So they have a number of different ways they can get water and put it in the system. They have a certain amount of demand they have to meet. And their prevailing thought for Jordan Valley was people in Utah, and this is correct, love to see water in the reservoirs. They recreate in the reservoirs. They like that when the water level gets low in the reservoir, people start feeling stressed that maybe we're short on water and and maybe we're heading into a drought. And so, for public reasons, and also to keep it in their mind as a safe storage area, they were favoring water out of the ground. They were using their wells and pulling water out of the aquifer instead of taking water out of the reservoirs. And they would every year leave acre feet of water in the reservoirs unutilized by the end of the season, and they would instead use the water in the ground. And we showed them the chart you can see on the screen there. The top two, the Jordan Valley Water Treatment Plant and the Southeast Regional Water Treatment Plant, are by far the two most efficient energy-wise sources of water. The amount of water used to treat, especially the Jordan Valley Water Treatment Plant, which is the largest, is so much smaller, order of magnitude smaller than you see these other wells that they've got in the ground. So the primary thing that they did was just change their view on how they use their water, and they realized that the water in the aquifer is a much better safe spot to leave the water. It's always there. It's easy to access. It's just underground, and to utilize their water shares in the reservoirs first, and that then shifted their production away from these wells and into the treatment plants, which dramatically lowered their energy burden. Another interesting thought on here is if you look at the list of wells, a lot of their newest wells with the highest efficiency motors and the best pumps are some of the ones at the bottom of this list. And the reason they're at the bottom of the list is because they're deeper wells. They have to lift the water much further to get them up to the surface. But if you talk to their engineers at the time, they just assumed these wells were the best wells. They were brand new. So one of their wells on here, the Willow Creek well, you can see it like the fifth one down, was a terrible well. They hated that well. It had sand issues, and so when they turned the pump on, it would pull sand up. So they had to run it partially constrained. It was just old pump, old motor. It was this dinosaur that they hated to use. But it was actually pretty shallow. The water was not too far down there, and so even with all of its imperfections, it was one of their better water sources. And when they realized that, from here, they prioritized and, in a sense, fixed that well. They put a new casing in, dug the well a little bit deeper so they can deal with their sanding issues. They put a VFD on it. They put some capital into it so that now this well, I'm sure if I saw an updated chart, would be even better because it has newer equipment. But they were able to just change where the water was coming from and save 25% of their energy. The next one I want to feature was a wastewater plant. This plant is in Boise area, the Lander Street wastewater plant. It was opened originally in 1950, and in 2016 they were deciding whether they should shut the plant down. Boise has two plants. They've got one on the west side, and then this one is closer to the center of town. And this plant does not treat its own solids, so they have a pipeline from this plant to the other plant, which handles their solids. And the idea was that they would just mothball this plant, decommission it. I guess I shouldn't say mothball. Decommission the plant, take it out of service, and just shift all the load to the other plant, the larger plant on the west side of the city. But they engaged with us, and we came in and found a couple of good opportunities for them. One thing that we often see in plants, particularly wastewater plants, is if the equipment's there, it's on, whether it's needed or not. And so you might have a plant that's built for, let's say, 30 MGD, 30 million gallons a day, but they're only operating at 15 MGD. You will still find almost everything turned on. And so we come through and ask the question. And in this case, they had both their banks of their UV light dosing on for disinfection, but their flow only warranted one of them. So they shut one of the banks off. And the question was asked, why are you using both if you can meet your permit with only one? Also, after their aeration basin came out, they had a dissolved oxygen residual of about 6, and they only required 2. So they were putting way more oxygen into their basins than needed, and so they lowered their oxygen. And in addition to that, they changed their aeration basin optimization. They shifted to a DO control, and eventually worked towards ammonia-based control, which is a much more efficient and effective way to control their basins. And then the last thing was that they had a pretty rampant use of their reclaimed W3 water, which I'll just take a quick moment to explain. Wastewater plants, the water, right before this final chlorination is sent out, so it's been largely cleaned, but it's not quite safe to be discharged. They call that reclaimed water, and they'll use it to water their lawn, or they'll use it to spray down the yard. They'll use it to spray all over. In fact, if I go back, you can see, this is an aeration basin. There'd be all throughout this, there'd be sprays of water just spraying just to knock down foam. And you see that all over a wastewater plant. Wastewater operators view that water as free water because it's their own water, and it's just water that they're going to choose to recirculate in their plant as opposed to discharging it. And we help them understand, and help, in this case, understand that water's not free because there's an energy cost to using that water. And so we work with them to reduce their reclaimed water usage, and therefore the pumping dropped off dramatically, and there was savings there. In the case of the Boise Lander Street plant, we reduced our energy burden by 17% just through operational changes. And as a result, Boise, because of these savings, Boise as an organization decided to keep the plant open and to continue to invest in it to provide the service to their residents. So it was a large success story for them, and also for the plant, and also for Boise, because they were able to continue to utilize this resource. The next example is this is my city of North Salt Lake, although that's not me in the picture. That's Sam Christiansen. So I was on the city council for this city for 8 years before I worked for North Salt Lake. But while they were engaged with Cascade, before I worked for Cascade, but while North Salt Lake was engaged with Cascade, excuse me, they were able to see a 25% reduction from their baseline in their energy use. And it came primarily from one item. I should explain. that North Salt Lake is built on a hillside. So this picture is looking down from above. This is from the hydraulic model. We found this when we were studying the hydraulic model. There's quite a bit of elevation gain here that you can't necessarily see. So on the left of your picture, you see a freeway. That's I-15, and that's down in the valley. And then coming towards the bottom right of the screen is quite a bit of elevation gain. So we go from I-15, the free interstate, up into the highest upper zone is about a 1,200 feet increase in elevation. And you can see there's these spots where you can see kind of blue fat T's. Those represent booster stations or tanks. And there's multiple pressure zones going up this hillside. I recognize not all of you are water professionals, so let me just briefly explain the pressure zones to you. Water, of course, is heavy, and so if you only had one pressure zone, the water at the bottom of the hill would just be, the pressure would be extremely high, and dangerously so, because the pressure from all the water above it on the hillside pushing down. So what cities do is they separate, going up the hillside into different zones, the water system. And in between those pressure zones are pressure reducing valves, or PRVs. The PRV is designed so that if, for example, there was a house or a series of houses on fire halfway up the hill, and the fire department came and connected to the fire hydrant, they could quickly deplete the amount of water in one zone. So a PRV is designed to look at the pressure downstream, and if the pressure gets too low there, then they open up and they flood that zone with water from higher zones as a safety measure. But operationally, you should typically keep the PRVs to restrict flow. You don't want flow to be always going down through those PRVs. But over time, they tend to creep open, because someone might complain in a pressure zone about, they might say, my pressure's too low. And they'll call the operators and say, my pressure's too low. And rather than figuring out the root cause of that low pressure, they just go out and tweak the PRV to allow additional flow from a higher zone. And paradoxically, that often makes the system worse, the problem worse. And so without really diligent review and maintaining the PRV settings, then you get what we found in North Salt Lake. So I've got a little video I'm going to show here. Let me explain it first. So what we're looking at is the water is flowing from the highest, the booster pump that listed as a booster pump. This is up by our golf course. It's the last leg of boosting in our water system. And it's boosting water from that pump up to the tank, which is the highest tank in the city. The orange dashed line that you can see is the boundary, roughly the boundary of this pressure zone, this higher pressure zone, the upper zone. And then going down the hill, it's listed as lower zone. There's actually probably 5 or 6 lower zones working their way down this hillside. So what we've done here is we've taken the hydraulic model and we've made it dynamic. So it's looking in real, so it's simulating the normal water use throughout the day. And our hydraulic engineers have they're putting essentially Kool-Aid in the water. They're saying, okay, if we add some dye right here, this is all, of course, happening just in the model. We want to see where that water goes. And so in the upper right-hand corner, you can see what percentage of the water in that pipe came from this pump. I'm going to turn it on now, and we'll see it. So essentially, you can see the water going where it's supposed to. That coloring is representing water working its way down the hill through all those PRVs that are not properly set. And what you're not seeing here is then the pumps are taking that same water and boosting it back up the hill so that it can leak down the hill again. And so all day long in North Salt Lake, they were pumping water up the hill and just in circles. It was just circling up and down. Obviously, there were uses happening as well. But it was extremely wasteful, and they just didn't know. This is a very common problem that we see in water systems. So here's the same simulation, but at this point, the PRVs have been set properly to try to keep the water in the higher zone. I'll start that simulation. And as you can see, the water stays where it's supposed to. Now, I didn't include a slide here, but there's right about where the word zone is a circle with 2 houses on it. The houses are, as you might imagine, at the top of this hill with a beautiful view. The houses are large, and the people that live in there have high expectations of the services they get from their cities. And in this case, the one house had actually purchased and installed their own booster pump because the pressure coming into their home was varied dramatically over the course of the day. And the reason that happened was because the city was not keeping water in the upper zone. It was leaking down through the PRVs throughout the course of the day. So after this change, that water, the fluctuation in water pressure dropped off dramatically, and now they get steady, high-pressure water all day long, and they were able to turn off their booster pump and just use the city water provided. And that only happened because we've now just adjusted our PRVs. I should say that this is a common issue we see all over the place, not just in North Salt Lake, but pretty much everywhere that you have multiple zones, we see this kind of behavior. Another case study for you. I'll try to finish up the case studies with about 10 to 15 minutes left, but I've got 2 more to mention. So this is the Kennewick, Washington wastewater plant. What you're seeing here is the daily model. I mentioned that we make an energy model for them. This is a daily model. The blue line at the top represents the energy that they would have used without making any operational changes. So this is us fitting their historical data with their historical energy use and now projecting in real time on a daily basis the energy that they would have used based off of these indicators in the model. And then the green line, which you see below, this is their actual energy use after they've implemented changes. So you can see initially it drops off quite a bit, and then they have this between March 17th and May 17th, they've got about a month and a half period of time where their energy use jumps up above, and then it gets back down into order and into operationally below the energy they would have used until the end. And I'm not sure what happened there at the end. This red line, or this kind of magenta line on my screen, this represents their cumulative savings over that time period. So, and in this case, down is good. So they start off, and as their savings continue, it gets steeper and steeper the bigger this gap is. You see during this section of time here where in the middle where their energy jumped, that the line goes up as well. I don't know if you guys can see my mouse, but I'm moving my mouse around. Hopefully you can be seen on your end as well. And then, of course, savings continue, and they end up having tremendous savings. In this case, actually, they I need to click on my screen again. Oh, some of the things they did. So this plant's a smaller plant. It's only a 5 MGD plant, and they had a bunch of aeration lagoons. And they adjusted their DO controls for their aeration lagoons, which had a huge impact. They were dramatically over aerating their lagoons. They chose to replace some pumps, so they installed some higher efficiency pumps. They had a flock basin where they were sending water through, and they were mixing, and they found that the flock basin was not providing any value, that they could get the same benefit without it. And so they completely bypassed the flock basin, and then they made a number of aggressive lighting and heating changes. I don't know if aggressive, but they found that they had outbuildings and with high energy set points or temperature set points. And so they just went and did kind of the stuff that you normally would think about with energy efficiency, changing out light bulbs and lowering temperature. They ended up with a 31% reduction in energy use from their baseline from implementing these changes, which was a huge success. And because of that, now their water system is now involved with SEM as well. So they were so happy with the results from their wastewater system that now they've enrolled their water system, and they're currently working their way through a bunch of opportunities at that site as well. The last example I wanted to show you was from the city of Blackfoot, Idaho, last case study. This is a city, 12,000 people. And before we got involved, they had implemented, they've got, I should give some context, they don't have elevated water storage in their city, which my guess is most of the cities in Oklahoma and Texas have a lot of in-ground storage, even though I do see when I'm down there elevated storage. But probably at this point, with how big your cities have gone, the elevated storage no longer can supply the need. So you have a bunch of in-ground storage, just like Blackfoot does. And so they use their pumps, their well pumps, as well as a booster pump off of their in-ground reservoir to establish pressure in the system. And just before we got involved with them, they had their SCADA operator put in a new control loop to control the pressure inside that in their water system, and it was tuned horribly. And so, as you can see in this picture, the pressure was just fluctuating dramatically. The pumps would all kick on, it would throw the pressure up, and then it would kick off because now the pressure is too high, they're overpressurized, and then the pressure would drop as use came in, and then they would kick our little pumps on again, and it would just swing all day long. And he even mentioned to me that at one point, the pressure spike was so high that in their elementary school, it kicked on the sprinkling system and flooded part of the school. So we came in and started looking to them, and immediately I said, "Oh my gosh, you got to slow down your control loop," which the operator he's not a control guy, and thought the faster the control the better, but in his case he was making it worse, and so we dramatically slowed down the response. We made it so that the pumps would consider changes over hours or half a day, as opposed to in a matter of instance or a matter of minutes. And you can see after the PID loop tuning that it dropped off their energy use nice and steady, even. They don't have these crazy swings, and it's a much less energy being used from that change. And in their case, that and some source selection changes resulted to them in 11% reduction in energy use. So our findings that as far as SEM, whether someone can benefit from SEM has no correlation with size, system complexity, or baseline energy use. Every system we've worked with, we found that there's opportunities for saving, and there's operational improvements that can be done that will help you save energy. And those operational improvements are, we've found, are best implemented through SEM because, as I mentioned before, the collaborative nature for water and wastewater systems and the positive peer pressure that exists through that process. So I appreciate you listening, and now I've got some time for questions.
Great, thank you so much, Matt. That was fascinating, very, very interesting to learn. So a reminder to the audience, there is a Q&A box. You can also raise your hand if you would like for me to turn on audio controls, but that can be tricky sometimes. One thing that immediately occurs to me, that last slide talking about that there's not a correlation between sort of context. A big part of the water conversation in Texas is that we both have too little water and too much water, and sometimes the same place can suffer from both instances,
right, where
water systems are overwhelmed by storm events and then experience extended periods of drought. And is your approach to these systems kind of better suited for, it seems like a lot of work that you've been doing is kind of in the western drier parts of the country, but can you think about ways that your approach can sort of help manage high water time situations? Yeah,
of course. Well, and that's a great question. So a lot of the work that I've done has been in the drier areas where drought is a concern, and so we talk about conserving water as a way to save energy. However, we have done a lot of work in the Portland and Seattle areas where often too much water is the order of the day or the order of the year, and so SEM works for both. As I mentioned before, when a system uses their energy better and treats their water and manages their pumps better, everything in their system improves. They're able to handle their water because more effectively, because they're properly treating their wastewater and not over-treating. That usually allows additional capacity, removes some of their capacity constraints. So during a stormwater event, They're better able to handle that. In the case of water systems, one problem that we frequently see with water systems is with their tanks. Water operators love to have full tanks. And so they'll just, if they've got a 20-foot tank, the pump will turn on to fill the tank when the water gets down to 17 feet, and it turns off at 19 feet, and it's just always full. And we help them understand that aside from the fire flow capacity, which is a certain percentage of that tank, the rest of it is designed to fluctuate throughout the day to meet peak demand with water storage as opposed to meeting peak demand with energy. So by adjusting those levels, they've got extra capacity in their tanks. And if they ever need to deal with water in a hurry and dump it someplace, their tanks aren't all full, so they can do that. And that helps them in high water situations. Or a situation where they're producing a certain amount of water. If they're treatment plant, water plants, they can't just shut off. And all of a sudden, the amount of irrigation drops off dramatically because you have a ton of rain that's come through. They can take that extra water as they turn down the speed of their plant, their production of their plant, and they can put that in their reservoirs because they're not all full. They're using them wisely instead of just keeping them full all the time. So those are all components of operating a system more efficiently, and that then provides better water quality, but also allows you to be better prepared to deal with system upsets like a drought or a high water event.
Mm-hmm. Yeah, it's kind of the general premise in efficiency of, if you have a better understanding of the state of your assets and how they're operating, you're, sort of better prepared in all cases.
Yeah. And one thing I'll mention, it is the rule, not the exception, for us to go in to water systems and ask them, how much energy do you use? Do you even look at your energy bill? And most water systems we deal with, the answer is no. They focus on delivering water, and there's an accounts payable department that deals with paying for things like energy. And so that there's almost always a disconnect between the energy being used and the cost of that energy from the operations and the administration of the operations, who aren't even looking at that. And so often the benefit comes just by increasing awareness, because now once the people running the water systems are tracking their energy use, maybe as a metric of the amount of kilowatt hours per million gallons treated, then they can start making changes to make that better. But in almost every case when we get involved, that's not even a metric that they're aware of. And so there's no way for them to make that better.
Absolutely, yeah. That is a I think pretty persistent challenge that I have experienced in just management of electricity bills and cost of electricity on just basic day-to-day functions in some communities. So I can imagine it can be amplified in a situation where the energy is being used to produce something that has been sold and creating revenue. It seems like a lot of the focus of the resources that you're providing to these cities is on kind of lower and no cost solutions. So do you find that you're able to identify low and no cost savings opportunities that pretty much covers the cost of the analysis, or kind of what is the payoff? Yeah,
that's a great question. So let me answer two things around that. The first, to answer your question, our average across water systems savings is about 10%. So we're working direct right now with a city in Utah. It's actually the next door city to North Salt Lake, my city, where we came in and we looked at their annual energy use and their energy spend. And we said, we don't know what we can help you save, but on average, we save about 10% when we work with water systems. And for them, that was a 1-year payback. The amount that we were charging, it was going to be 1 year for them to recoup that cost. But let's say worst case scenario, they only save a quarter of that. That's still only a 4-year payback, which is, I mean, maybe that's not the worst case scenario, but it's still, it's pretty rare that we don't save 2 to 3% at least. So even still, that's a 4-year payback, which is better for most cities than many of the investment things that they do, and the efforts that they do to improve their system and operations. And that's similar on a larger scale to the engagement we have with Phoenix, where it's a 2-year operational improvement. We've made a commitment to help them save 7% of their energy use, and that if they save 7%, that will pay for our entire engagement, 2-year engagement. It's a 2-year payback for them. So we find that the energy efficiency in water systems has a great payback because there are so many opportunities. Now, the other side to the question you didn't ask, but I at least still want to answer is, even though our focus is on low and no cost changes to operations, invariably we find a lot of capital opportunities that should be pursued. And so as part of the opportunity list that we provide, opportunity register that we submit, or we help the city submit to their energy team and to their organization, there's a list of long-term capital improvements that they should consider. And so those things then get on their 2 to 3 to 5 year plans for implementation. So once again, those are then business decisions made by those organizations, but it helps them seed their capital plans with projects that have a return, have the energy efficiency return. So it's not just that we're going to come in and tweak how you operate your valves and your pumps and your reservoirs. We do that, but we also then leave them with a list of long-term objectives that they should pursue to achieve even more savings.
That was, in fact, going to be my next question. So you read my mind. Yeah, from what I understand, a major challenge in probably water systems across the country and in Texas in particular is transmission leakage and transmission, and basically, kind of major infrastructure needs in water systems. And so it sounds like that may be part of the sort of insight that you generate for your clients as part of the process. Yeah.
And along those lines, people often, you think about lost water through a pipe, and that's terrible, right? It's a waste, and people think of it on the order of the wasted water, but often don't think about the energy that it costs to get that in that pipe, excuse me, at that pressure. And so we bring that up. We talk about the energy cost associated with a leak in a pipe or a leak in a tank, or even a broken vacuum valve that's just leaking water all the time in your pump house. All those things we talk about because there is an energy cost to those.
Absolutely. Well, good. If there's no questions from the audience, I think we can leave it there. I really appreciate it. That was very interesting and informative, and I'm really glad to welcome you to SPEER as a member, and that your expertise and insight will continue to support the work that we're doing down here in Texas and Oklahoma.
Awesome.
Yeah,
well, thank you for the opportunity.
All right, absolutely. Thanks all, and we'll see you in January. Have a good one.